Today, we're going to dig into a cornerstone of quantum physics, Compton scattering, but we're going to look at it through a really radical new lens called dynamic vacuum field theory, or DVFT for short. You see, this theory, it challenges the very way we think about what a particle even is, and how the universe works on the most fundamental level. So let's dive right in.
Okay, this is the big question. This is the idea that DVFT puts right in front of us. It asks you to kind of forget everything you thought about the vacuum being this empty, dead space. Instead, what if the vacuum is a real, physical thing, a medium? And everything we call a particle, well, that's just a disturbance, an event happening inside that medium.
All right, here's our game plan. We'll start by unpacking this new idea of the vacuum. Then we'll see how it actually derives the famous Compton formula from scratch. After that, we're going to put it to the test, 3 of them in fact, against real-world experiments. And finally, we'll look at the really exciting part, where this theory might point to brand new physics.
So let's really build this new picture from the ground up. You know, in standard physics, we think of the vacuum as this empty stage where particles dance around and interact. Well, in this model, that's just completely wrong. The vacuum isn't the stage, it's the main character.
Okay, so here's the math behind it. The vacuum is described by this complex field. Now, you don't have to be a mathematician to get the gist. The important thing is that it has 2 key parts. That first bit, the amplitude, you can think of that as the stiffness of the vacuum, its inertial density. And the second part, the phase, that's what dictates how waves, like light, can travel through it.
And this is where it gets really cool. In this framework, a photon isn't some separate little bullet of light. No, it's just a ripple, a wave, traveling through the phase of the vacuum. An electron, on the other hand, is totally different. It's like a stable, localized knot or a defect in the very fabric of the vacuum itself. So you see, they're not 2 different things. They're 2 different behaviors of the exact same underlying field.
Look, a new idea is great and all, but for it to be actual science, it has to connect with what we already know works. It has to match established, proven physics. So let's see how DVFT does when we try to derive one of the most famous results in all of quantum mechanics.
And this is absolutely crucial. DVFT isn't just pulled out of thin air, it's built on solid ground. It respects one of the most profound and beautiful principles in all of physics, Noether's theorem. All this really says is that if the laws of physics are the same here as they are over there, if the theory is translation invariant, then energy and momentum have to be conserved. It's a non-negotiable.
And boom, there it is. This shows you the power of that principle. By just applying conservation of energy and momentum to the interaction between our vacuum wave, the photon, and our vacuum defect, the electron, this exact formula, the one that's been verified countless times in experiments, it just emerges naturally. We didn't need any new physics, just a completely new way of looking at it.
So the math checks out on paper, but how does it stack up against real, actual experimental data? Let's kick off our validation with a classic low-energy X-ray scattering experiment.
Okay, so the source material we're looking at points to a Liebold physics leaflet. In their experiment, they measured a wavelength shift of 4.9 picometers, plus or minus an uncertainty of 1.3 picometers. Now, when we use the DVFT framework, which, remember, gives us the standard Compton formula, the predicted shift is 4.414 picometers.
And there you have it. It's a perfect match. The value that the theory predicts falls right smack in the middle of the experimental error bars. So for our first test, DVFT passes with flying colors. Now let's crank up the energy and see if it still holds up.
All right, next up, we're boosting the energy and looking at gamma rays. For this check, we're going to use a set of what they call typical tabulated values from an Ortec lab manual. This gives us a really high-precision benchmark to compare against across a bunch of different angles. What's just so striking here is how incredible the agreement is. We're looking at a 662 keV photon coming in, and we can compare the observed energy of the scattered photon with what DVFT predicts at different angles. And that column on the far right, well, it tells the whole story. The percentage difference is just tiny. We're talking fractions of a percent.
In fact, if you look across all the data points in that Ortec manual, the maximum deviation, the biggest difference they found, was less than 0.3%. This isn't just a good fit. For a typical dataset like this, it's an absolutely exceptional demonstration that the underlying physics are spot on.
Okay, for our final test, and this is the most demanding one, we're going to the absolute extreme, the ultra-relativistic regime.
This is where a super high-energy electron smacks into a low-energy photon and boosts it to just incredible energies.
So for this, we're looking at data from the new Subaru Accelerator facility. In one of their experiments, they took 1 GeV electrons and smashed them into a laser beam. What they saw was a maximum scattered photon energy, what's called the Compton edge, of about 17.6 mega-electron volts. And the DVFT prediction? 17.54 MeV.
I mean, come on, that is an astonishingly close result. Getting an agreement at the 0.3% level in this kind of high-energy environment is just a massive confirmation. So let's recap. Across 3 totally different energy regimes, the kinematics that fall right out of this DVFT framework perfectly match what we see in the lab.
So, if DFT just perfectly reproduces all the existing results, you might be sitting there thinking, okay, so what's the point? And that's a fair question. The point is that a truly great theory doesn't just explain what we already know, it predicts things we haven't seen yet. The most exciting part of this whole new framework is where it might actually deviate from the standard model, pointing us toward new, undiscovered physics.
And what's great is that DFT gives us concrete, testable predictions. It suggests that if you hit an electron hard enough, it might stop acting like a perfect little point and start to reveal some of its underlying structure as a vacuum defect, what physicists call a form factor. The theory also predicts that an electron's mass might seem to change depending on the photon's energy, or that the vacuum itself might start to behave in really strange, nonlinear ways if you hit it with an extremely powerful field. These are the kinds of predictions that could really set it apart.
And that brings us right back to where we started, but now we're standing on a pretty solid foundation of evidence. Dynamic vacuum field theory makes a really compelling case that everything we see, particles, forces, the whole shebang, might just be the complex behavior of a single underlying medium. It is a profound shift in how we see the world, suggesting the vacuum isn't just where the show happens, it is the show.